In our next section for Layer 2 VPNs, we're going to talk about hierarchical VPLS or VPLS, which is a scaling feature that's designed to get past the problem of doing a full mesh of tunnels between the provider edge routers that are servicing the emulated LAN. So if we take a look back at our diagram where we left off previously and talk about just the overall logic of what the VPLS is trying to do, we had a case where we had 3 different PEs. We had router 2, router 4, and router 5. And we were trying to bridge traffic from router 1 over to router 7 and router 8 and vice versa, which means that we had to form a tunnel between router 2 and router 4. We had to form a tunnel between router 2 and router 5, and then likewise between 4 and 5. Now, when we compare this to the MPLS Layer 3 VPN deployment, the main difference from a provisioning point of view or an operations point of view is that if we wanted to add an additional site to L3 VPN, we don't need to modify the configurations on the existing PEs because they already have the route target import and export policy that's going to allow them to learn the routes that are advertised from the new provider edge routers. But in the case of the VPLS, that's not necessarily true. That if we were to add, let's say, a 4th PE, and we have router 11 over here that's maybe talking to some other customer edge router, we would then need to touch all of the other PEs, go to router 2, provision a new pseudo wire over to 11, then from 11 to 5, from 11 to 4, etc. So the main problem then is that as you start to add customer sites, the amount of tunnels that you have to form is going to be prohibitive both from an operation point of view and then also from a scaling point of view of the control plane, how many different circuits that the box needs to maintain, how many labels that it is going to have, and ultimately the systems are going to have an upper limit as to how many pseudo wires that they can actually hold on the individual line card or in the control plane as a whole. So basically then what VPLS is going to do is going to change the network into kind of like a hub and spoke type topology, where we're going to split the network into 2 different roles, where previously we just had our provider edge routers. Now we have 2 levels of hierarchy. We have the user-facing PEs, which are called the UPEs, and the network-facing PEs, which are the NPEs. Then we're going to peer from the UPEs to the customers. We're going to peer from the UPEs to the NPEs, and the NPEs are going to peer to each other. The end result is that we have a hub and spoke hierarchy, or what is sometimes referred to as an E-tree topology, as opposed to our E-line, which was the virtual private wire service, the point-to-point like Atom-based VPN, versus the E-LAN, which is the regular VPLS that's a full mesh. And now we have this E-tree that is multiple levels of hierarchy. Now, we'll see from a configuration point of view, there's not really much difference between a regular VPLS and HVPLS. What's really changing is behind the scenes, what's happening with how traffic is forwarded between the different circuits in an HVPLS. Now, with the regular VPLS, there's a basic split horizon logic that says when I receive a frame in a pseudo wire or in an X-connect that is belonging to that particular bridge domain, I'm not allowed to send the packet out another pseudo wire that belongs to the same bridge domain. Basic logic being that if we have 3 different PEs, if we have routers 1, 2, and 3 that are servicing customer edge respectively 1, 2, and 3, and let's say the customer edge 1 is sending a broadcast packet into to the layer 2 network. So it's going to all Fs. It goes over to router 1. Router 1 is going to send this over the pseudo wire over to router 2. It's going to send it over the pseudo wire to router 3. And then they're then going to deliver it towards their customer edges, so to their attachment circuits. Now, if router 2 were to take this broadcast frame in and then forward it over to 3, and then likewise 3 was to take it in and forward it over to router 1, this is where we would effectively create an infinite loop in the layer 2 network. Reason why is that spanning tree does not go inside of the VPLS. So the simple rule is basically saying, well, instead of using spanning tree, we're going to do basic data plane forwarding logic that says, I receive it in from the core, don't forward it back out to the core. So it can come in from the edge and go to the core, or come from the core and go back to the edge, but not core to core. Now that works fine as long as the PEs are fully meshed, which in the case of HVPLS they're not going to be, which means that we need to change this forwarding logic around a little bit. Specifically, what's going to change is that we're going to selectively disable split horizon. So now we have these 2 separate roles where we're now going to have our customer edges. So let's say we have CE1 and CE2 and CE3. Okay, these are connected to our user-facing PEs. So we have UPE3, we have UPE1, and UPE2. So those are the physical attachment circuits. This would be like our last mile circuit, the physical Ethernet port going to the customer. And then we have in the core of the network our network-facing PEs. So we have NPE1, we have NPE2, and then NPE3. So the user PEs within that physical region, normally based on the way that the physical service provider network topology is set up, kind of similar to how a route reflection design would work, that the local UPEs are going to peer with the NPE. The NPEs are then going to peer with each other in a full mesh. And the case that we have, let's say we have another UPE here, let's say number 4, that's going down to customer edge 4. And let's say now that we have a broadcast packet that comes in. So it comes in from the customer, goes to the user-facing PE, it forwards it out the pseudo wire. So this is an X connect, okay, that's the layer 2 circuit that goes over to the NPE. NPE says I'm gonna flood it out this direction, but when it gets to NPE 2 and 3, they're not going to send it to each other. Okay, so split horizon is going to be enabled on this interface, or not that interface, but that logical association is the logical X connect between the two of them. But then when the NPE receives the traffic from another NPE, so from the core to the core, they're going to move it down towards the edge. So the end-facing PE is going to send it this way to the user PEs, and then the user PEs send it down to the regular customer edge. Now, the difference in the behavior here is that this is coming in an X connect and essentially going out another X connect. So this means that from the network-facing PE point of view, they can forward frames, broadcast frames specifically, to user-facing and to network-facing PEs, but a network-facing PE will not forward traffic from one NPE to another NPE. Now, the potential problem with this from an implementation point of view is that it's up to us to decide where split horizon specifically is going to be enabled or disabled based on the configuration. So if you misconfigure this, the CLI is not going to tell you that there's a problem. Just the end result is that you do actually cause a loop in the network, and then you could potentially either cause problems in the control plane with the looping or cause problems in the data plane where you eat up all the bandwidth based on a broadcast link. Now, as we talked about before, from a syntax point of view, there's two different ways to configure this. We have the legacy syntax, which let's actually take a look at the CLI here real quick, where the legacy syntax is under the L2, I think it's L2 VFI. And we say that L2 VFI is manual. And then the VPN ID is whatever, 1, 2, 3, 4. And again, we'll review what these specific syntax options are doing. And then we say the neighbor is 1, 2, 3, 4. The encapsulation in this case would be VPLS. And then we can say, do we want split horizon to be on or not? Okay, so this would be what the legacy syntax would look like when we are configuring the link from the NPE to the UPE. So again, the point being is that we receive it from the core, we need to forward it to the edge, but we don't want to forward it from the core to the core X connect. Now, the newer format of the syntax doesn't use this specific command, which can make it kind of confusing where split horizon is actually enabled or not. And it depends on the IP address of the X connect. Is that listed under the bridge domain, or is that listed under the virtual forwarding instance? So let's take a look at where this is documented in terms of syntax-wise, and you'll see what I mean here in a minute, how this can get kind of confusing. Okay, so from the main documentation page, we're going to go to Products, to iOS. And let me just jump ahead here to iOS XE. Under our config guides, and then this is going to be under MPLS, multi-protocol label switching, and then again under layer 2 VPNs. So this is going to be under HVPLS PE redundancy, and then also under just virtual private LAN services. Okay, so under the second one here, which is just the basic VPLS configuration, under HVPLS, it says reduces signaling and replication overhead by using a full mesh and hub and spoke configurations. And the hub and spoke configuration operates with split horizon to allow packets to be switched between pseudowires. Configuration operates, that should actually say without split horizon, to allow packets to be switched between pseudowires, effectively reducing the number of pseudowires between the provider edge devices. Okay, so let's see if they have a config example here of what this is supposed to look like. Now, they have the full mesh config, but not the, let's search for no split horizon, see if they show an example, which would basically be this. Okay, this configuration here would be the one that is on the NPE, where, again, there's two different roles. User PE is the one closest to the edge, that's physically attaching to the customer. NPE is the one that's in the core. So this particular device would be considered an NPE. This pseudowire and this pseudowire would be going to other NPEs. And then the one that has split horizon disabled on, this would be the one that's going towards the user-facing PE. But from a syntax point of view, it doesn't really tell you this is the particular role and where you need to do the configuration. You can figure this out, though, based on if you were to draw the topology out and try to think about where would split horizon need to be enabled in order to stop the loops. And specifically in this case, it would need to be enabled on these three circuits here in the core of a full mesh. But we want to be able to receive traffic in this circuit and forward it out that one. That's why this is the one that has to have no split horizon enabled, okay, or split horizon disabled, I should say. Now, when we look at this in the, not the legacy configuration, which is the L2 VFI, if we look at it under what they're calling the alternate configuration, which is the L2 VPN VFI, which is then calling the bridge domain, the difference here is that these interfaces that are listed directly under the bridge domain, those are the ones that are going to have split horizon disabled when we're listing a specific XConnect destination. Now, we will be able to see either way when we look at the show VFI or the show L2 VPN VFI, whether split horizon is on or off. But we'll see it can be kind of confusing from the config whether it is actually going to be working that way. Okay, so first I'm going to show this with the legacy syntax, and then we'll look at the new format so we can tell the difference specifically. Okay, so what we're going to be doing specifically, if we look back at our diagram, is that router 2 and 4 are going to be user-facing PEs. Okay, so they're facing the customer edge router, so router 1 and router 9. Router 4, likewise, is facing towards a customer edge. Router 5 is facing towards a customer edge. And then the core of the network is going to be router 3, which is an NPE, and then router 6, which is an NPE. So we're going to have a pseudowire that goes from router 2 to router 3, one that goes from 4 to 3, one that goes from 5 to 6, and then the core to core pseudowire is going to be between router 3 and router 6. Now, in this case, we don't have another router up here that would be another network-facing PE that would show us whether split horizon is being disabled or not. But again, it's going to be on this pseudowire here, this pseudowire here, and this pseudowire here. These are the ones that we have to have split horizon disabled on. The one between 3 and 6, and then whatever other NPEs in the core, that's where we want it enabled, which it is by default. Okay, so first things first, we need to configure the attachment circuit that's going down to the customer, which again, based on our configuration that we were doing earlier, that's where the service instance is going to be. So on router 2, we're going to say that on our gig port, gig 2, if we do show run interface gig 2, we're going to create a service instance. We'll say this is instance number 1. And the encapsulation is going to be default. So it's just going to be all layer 2 traffic. Okay, so same thing on router 4 and router 5, which are facing towards the customer edges. Okay, these two down here. 4 and 5. Okay, next we're going to create the layer 2 VFI, and again we're going to do this first based on the legacy syntax, and then we'll look at the one after that. So let's say full mesh configuration, which is we have the L2 VFI. We're then specifying the neighbors and then calling the bridge domain. Bridge domain is going to be the one that is mapping to the attachment circuit. So if we look for, let's see if it shows the actual bridge domain config. And this is unfortunately one of the problems with these documents under VPLS. They don't really show a full end-to-end example with all three of the pieces fitting together, which is the attachment circuit to the customer, the bridge domain, which is mapping the attachment circuit to the virtual forwarding instance, and then the VFI, which is actually mapping to the remote X connects, which is basically this one here. So they're calling this configuring VFI on a PE device alternate configuration, which is the one that we were doing previously, the L2 VFI. Okay, and there's a question, which link did I use? This is the one that's the regular VPLS. Okay, this other one that is the HVPLS redundancy, this is talking about basically just additional pseudo wires in the core, like you have a full mesh between these. And then in terms of the configuration for this, it actually does show the full thing here. So let's see if they show an example. Config example for each VPLS NPE redundancy, which would be, this is the new format of the syntax. And then we have the service instance. So actually, yes, this one does basically show all of it. Okay, but we'll come back to this example in a minute. So we have the service instance, and then we're going to put it in the bridge domain. Okay, so let's say we have bridge, is it dash domain? Dash domain, we'll give it a number. And we'll say that the member is going to be gig 2, and it's going to be the service instance on that, which in this case is 1. Okay, if we then look at the show bridge group, or excuse me, show bridge domain, what we should see up to this point is that we should start learning the MAC addresses of the customer edge router or the customer edge switches. Because again, if you're not learning any MAC addresses on the attachment circuit, the physical link down towards the CE, then we won't be able to bridge any of the traffic that actually goes to the pseudo wires into the core. Okay, so only a couple commands so far. If we look at the show run interface gig 2, and then the show run pipe section bridge, we're binding the two of those together. Okay, so this same config is going to go on 2 and 5 as well, or 2 and 4 as well. Okay, the difference between the two formats of the syntax now is that with the legacy version, we are going to bind these together under the, and actually this, let me search for no split horizon again. Under L2 VFI. Okay, then we're calling the bridge domain. So in our particular case here, if we look back at the diagram, from router 2's point of view, it's going to say the neighbors are 4444 and 5555, and then likewise the opposite direction. Okay, so let's just edit this, this syntax here. So we're going to say that we're configuring the VFI. They gave it a name of VPLS-B. We're giving it a VPN identifier, which again is used in the BGP signaling to figure out the route distinguisher and the route target value. So you need to make sure that this matches between all members of the same VPLS. Same as like an L3 VPN, you need to match the route target import export policy. That's effectively what this is doing here. It's their endpoint identifiers. Okay, so in our case, the neighbors are, from 2's perspective, 4444. And, or actually, excuse me, no, this is going from, we're going from 2 to 3. Okay, so neighbors 3333. And then, let me save that other command for later. The bridge domain number was bridge domain 1. Okay, so let's just keep it a 1 for simplicity. And we'll call this just VPLS. So this config is going both on router 2 and router 4, which are the user-facing PEs. Okay, so 2, bridge domain, what did I call it? Bridge domain 1 is not configured. Bridge domain 1 is configured. Let's see, show run section VFI. Okay, so under the L2 VFI, bridge domain 1. This must be calling a different syntax of the bridge domain. Okay, let's see what it says under see, this document doesn't show the older syntax. Let me try on this one again. So it's creating the bridge domain. It's specifying the member, which is what I'm doing here. I wonder what that error means. Okay, let's say show run section bridge or VFI. Let me try this. Okay, it may need to be under the VFI. We may create it here when we specify the bridge domain. So let's say bridge domain 1. And then it must be an order of operations issue. So then bridge domain 1 has that as the service instance. Please use bridge domain command under this service instance. So, okay, so it goes at the port level is what the legacy syntax is. So under the interface, show run, interface, gig2, service instance, and then that's where the bridge domain goes. Okay. So let's say show run section bridge or VFI. Gig2. Okay, so same thing is going to be then on router 4, which is basically this. Okay, so on 4, no bridge domain 1. There we go. Okay, from router 5's point of view, same syntax, except we're going to a different N-facing PE, which is router 6. So that's going to go on 5. Okay, let me delete the global bridge domain. And then the difference now is going to be that in the middle of the network, router 3 and router 6, they don't have any physical attachment circuits. They're just bridging pseudo-wire to pseudo-wire. So we're going to have the virtual forwarding instance that's still calling the bridge domain, but it's going to be just for the XConnect neighbors. So if we look back at their syntax example, this is where we would have to disable split horizon. So on router 3, we would basically say that we have the VPLS. Okay, we'll say that this is our NPE. The neighbors are 6, encapsulation is MPLS. The neighbor is also 2, encapsulation MPLS, but this is where we have no split horizon. Another 2, and then also to router 4. Okay, it should look like this. From 3's perspective. Okay, we should then see we're going to form a targeted LDP session between them because remember, unless we're doing the BGP auto discovery and the BGP signaling, when we specify the neighbors manually, the point of that is saying that's going to be the target of the LDP tunnel. So from a control plane signaling, it's going to be the same as what we had previously. If we look at the show MPLS LDP neighbors, we should see that we have targeted hellos, okay, that are going between all the neighbors. So from us to 2, from us to 4. Now it didn't give us a log message here that the neighbor came up because we were already running IGP plus LDP in the core. But now we're going to have 2 levels of labels, one for the outer transport label and then one for the inner L2 VPN label, which is going to be the VPLS label. Okay, so router 6 is going to say the same thing where it's going over to router 3. And then the one that's going towards the edge is going to router 5. That's the one that we're disabling split horizon on. Okay, Okay, so on all of these now, we want to look at simply the show virtual forwarding instance, the show VFI. What this is going to tell us here is split horizon enabled or not. So from router 6's point of view, which is the NPE, it's saying that the circuit going over to router 5, which is the user PE, does not have split horizon on. But the one going towards the core to another NPE does. Okay, same thing should be true from router 3's perspective. It's saying the ones that are going towards the edge do not have split horizon on because we want to be able to forward traffic between these two, but the one that's going to the core does have split horizon on because we don't want to receive a broadcast in from the core and then send it back to the core. We want to receive it from the core, send it to the edge, or likewise receive it from the edge and then send it to the core, eventually to go to the other edges of the network. Now, from the UPE's point of view, they're going to have split horizon on all of the circuits because they're only peering with the, they're peering down with the customers and they're peering with the NPEs. So if we had multiple NPEs, we would not want to receive traffic in from them and then send it back to the core. That's effectively where we can cause the loop in the network. And that's what this document is talking about here, which is the NPE redundancy. Because figure if in the core of the network, if we have just one network-facing PE that everyone is peering with, if that box goes down, then you lose access to all of the customers. So you want to make sure for redundancy that you have multiple devices in the core that you're peering with, but it also makes the split horizon design more complicated because if you accidentally turn it off on the wrong circuit, that's when you can cause a bridging loop in the core. Now, once we're done with this example, we'll come back and show the one here, which is the L2 VFI. The problem with this, though, is that unless you knew which one has split horizon on or off, you can't really tell based on the config here. You can tell when you look at this output, which is the show VFI, and it tells you yes or no, is it enabled? But if you were to accidentally do these the opposite direction, then it's not going to work. Okay, so let's look at the final result, is that if we look at the show bridge domain, we should see on the edges of the network, like router 2, that we're learning traffic in from the physical attachment circuit. Okay, same should be true from router 4's point of view. We're receiving traffic on the gig link. We should also be receiving it on router 5. Okay, then when we look at towards the core, router 3 also needs a bridge domain to be created. So let's say show run pipe section L2. So we'll say that we have a bridge domain. Okay, the bridge domain is basically the MAC table. And then the same on router 6. Bridge domain number 1. Okay, if we show bridge domain 1, we should be learning the MAC addresses. And it says that we have the pseudo wire, or the MAC addresses are being learned in the pseudo wires to the towards the user PEs. And then we're doing a static forwarding of the broadcast, basically out all of the circuits. But again, it depends on whether split horizon is enabled or not. So there was a question here. Split horizon should be applied between the NPEs, correct. So the core to core facing links, that's where you want split horizon on. From the core towards the edge, that's where you want split horizon off. So the only place in the place that you are disabling it, if we look at their diagram, is when we go this direction. So towards the user, okay, the user is attached to the customer edge. This is where we want no split horizon. This one here, that would be going, well, technically it's not this guy. It would be going here to here. Since these would be in a full mesh, that's why we need to enable split horizon. Okay, likewise, from the UPE facing towards the NPE, split horizon is enabled, which is the default behavior, because what we're trying to prevent, again, is the fact that a broadcast comes in here, we send it out to both NPEs. If they send it to each other, that's where we would cause the loop. So we need to make sure it goes this direction, but then not to each other. Okay, this should be denied. And then we go towards the users. If the user was to loop the traffic back in, then likewise we would cause another loop here. So split horizon needs to be enabled in this direction. The only one that it is disabled on is when we're coming in from one user PE, and then we want to go back to another user PE.